welcome to our joint colloquium from ASIAA down the road. We are very happy to have Chao-Lin here today. So, as I always say, astrophysics, astronomy eats a lot of budget. Physics people always are upset that we eat so much budget. But I have to say, the reason is that our laboratory begins on the surface of the Earth and goes to the edge of the universe, as you see. Not only do we sample all volume, all space, but all time. So that's why we deserve so much budget. Okay, so Chao-Lin is here. He is going to tell us about these wonderful results for BICEP2 that everybody already has heard about. But a few important things to note why everyone is so excited, of course, because Chao-Lin is one of our Taiwanese products. And he came from the best school in the country, right? From Taiwan. And then he went on to Berkeley, another good school, Caltech, not a bad school. And then found his home now at Stanford University, working on the microwave background. As you all know, the microwave background is the signature from the expansion of the universe, but we did not know how to prove the inflation theory. So here's the first experimental data to tell us whether we can trust the inflation theory as the theoreticians will have us believe. So the other thing important to remember is that Chao-Lin actually started as a theoretician, but found a way to experimental science. So here he is. Let's welcome him.
It's a pleasure to be here. So I'm going to talk about BICEP2 results, implications, and future of cancer cosmology. The subtitle of this talk is, it's really an amazing combination of three big ideas, theoretical ideas: inflation itself, and how inflation generates gravitational waves, and how gravitational waves get detected by generating remote polarization in the microwave background. And also, in combination with amazing technology and dedicated experimental programs. And some human element, focus, teamwork, faith, etc. So another amazing thing is we get to do all of this at the South Pole, one of the most exotic places on the planet. Here's a picture of our neighbor, South Pole Telescope. You can't quite see our small experiment next to it, but it's doing much bigger science and big picture. I can see Aurora here and the Milky Way. So the basic experimental approach is, you heard about cosmic microwave background as the most ancient light. But if you want to study inflation, it's not ancient enough, because cosmic microwave background is also a curtain blocking the very beginning. The surface of last gathering was at 400,000 years old, when the universe was at 400,000 years old. So you need something that can travel across the entire universe to study the very beginning. That is gravitational wave. So we use gravitational wave to study the beginning, or inflation. And photons can't quite do that, because it's a wall of radiation coming at you when the universe was already not that young. So the approach is to, so this is kind of a wall blocking, everything before 400,000 years old from our view. And and but gravitational wave can just travel across that opaque, ionized medium. So the question is, how do you detect gravitational wave? Well, the nice thing is gravitational wave leaves a very distinct imprint in the polarization state of microwave background, and that's how you do it. Gravitational wave leaving an imprint in microwave background, and this is what we observe. So we're looking at an image of gravitational wave imprinted on microwave background, and that gravitational wave was generated directly at the bang of Big Bang or inflation. By the way, this is now the official BICEP2 version of the history of the universe that you should feel free to copy and ditch the WMAP and Planck. So the first big idea is inflation. So inflation was proposed in the late 70s and early 80s to solve a few classical cosmological problems. Many of you have heard of it, and I'll just give you one example here, and that is the horizon problem. So basically, why was the universe started out so uniform, even though they didn't have time, different regions didn't have time to talk to each other and get into equilibrium. So if you trace the trajectory of a test particle, in this case a galaxy, you realize the horizon size, which grows as c times the age of the universe, c being the speed of light, grows linearly. And if you trace to earlier time, all of this stuff will be, basically coming into the horizon. Okay, meaning at early time, these regions didn't have time to really talk to each other, and yet when they appear on the horizon, they appear to be uniform. So different regions look the same. So the way inflation solved it is to move all these trajectories below the horizon scale at the beginning, right? So you this is how you do it, and now all of a sudden there was time, different regions to thermalize and appear the same, basically. So this is how inflation solved the horizon problem. In other words, if you look in, this is still time, so the scale of the universe has to undergo a rapid expansion, right? So this is a very rapid expansion because time is this way. So inflation solved the horizon problem by resorting to exponential expansion of space. So you probably heard of that, but if you just hear about it today, it takes a little thinking to understand that. It's a very difficult concept. So how is it achieved? So many of you have seen this equation. This is the famous Einstein equation for gravitation. But if you haven't seen it, it's okay, because it's completely analogous to the Newtonian version, the Poisson equation, where phi is the gravitational potential and rho is the matter distribution of the density. And this is just that. So in Newtonian limit, this reduces to that. This is the general relativistic version of it. So if you take the energy of a scalar field, it seems foreign, but it's exactly the energy of a spring, if you think of it this way. In fact, it's completely identical to the energy of the spring, okay? And if you take the energy of the spring and you calculate the tension, and so on, the kinetic energy and all of that, and you plug into the right-hand side of the Einstein equation, you get exactly an exponential expansion. So it's just as simple as that. It's completely classical. So as long as you have such an object, a scalar field with a pretty generic energy form, you have inflation. Okay, so there's no quantum mechanics or anything like that. It's So if the scalar field changes very slowly, or it satisfies the so-called slow roll condition, you get a constant expansion rate, or A dot over A, the Hubble parameter. And that gives you a constant exponent, and it's an exponential expansion that solves this problem. So it's a very simple concept. You only use general relativity, basically. And what you get is the energy scale of your string or scalar field gives you the expansion rate. In addition to solving the classical cosmological problem, inflation does a very nice thing. It generates perturbations. Okay, and this is the part that we talked about. You know, a connection, deep connection between quantum mechanics and the cosmos. Okay, and prior to BICEP2 results, the properties of the scalar perturbation, this is one of the two types of perturbations generated by inflation, became the strongest evidence for inflation, actually, because people started to question the naturalness of how inflation solved the flatness and horizon problem and so on. Okay, so in the end, it was the property of the perturbation that really gave inflation very strong support before BICEP2 results. So these properties are so the perturbation, because it's entirely coming from a single scalar field. It has to have only 1 degree of freedom, or it's an adiabatic type of perturbation. All different components fluctuate the same way, and the fluctuation has to be Gaussian distributed, and the spectral index is close to scalar varying. So these are the pillars of inflation, if you will, before the gravitational waves were detected. So this is a schematic view of how fluctuations were generated by inflation. Even in vacuum, during inflation, the uncertainty principle demands that there is 0-point fluctuation, okay, in all the fields. So the fluctuation in the inflaton field itself gets inflated and amplified, if you will, to create the density perturbations discovered by Kobe and very well studied by Planck, WMAP, SPT, and galaxy surveys and so on. Became the seed of structure formation, and that grows, the fluctuation grows under gravitational instability, creating clusters of galaxies, planet, people, animals, and so on. So that part is very well known. So another part that's very well theoretically motivated is the vacuum fluctuation of gravitation itself, or if you will, the ground state of graviton. Okay? So if gravity is quantized, there will be vacuum fluctuation in graviton. And that part will be inflated and amplified, just like the inflaton field was. And it creates a gravitational wave background. And we believe we've just detected this gravitational wave background. So by doing so, we completed the inflation paradigm, and we set the energy scale of inflation, okay, at the grain unification scale. A little bit of more physics, because this is a physics flow, right? So if you take that Einstein equation and you linearize it, so you've done this in classical mechanics, and you get a harmonic oscillator. And in this case, it's very similar to harmonic oscillators, except for the expansion term, okay? Without the expansion term, it looks just like a harmonic oscillator. It gives you a plane wave solution. There are two types of plane waves, so these are very complicated tensors, right? So you get one scalar type perturbation, and you get a tensor perturbation, which is a gravitational wave. So the form of the solution looks like this. So without looking at this part, it's just very similar to plane wave, but in an expanding universe. However, with the expansion term, when for a given scale, okay, when that scale gets beyond the horizon scale, perturbation becomes frozen. The amplitude of the perturbation becomes frozen. So this is a very simple linear solution to the linearized Einstein equation under the simple inflation background. Okay, so it's all classical mechanics, all classical physics again. There's no quantum mechanics or anything like that. However, for a given field with a plane wave solution, if you combine that solution with uncertainty principle, you know the expectation value of that plane wave cannot be zero. All right? So the RMS value for that linear, for that plane wave is assigned by Heisenberg's uncertainty principle. So likewise, combining this linear solution with uncertainty principle, you fix the RMS or the expectation value of the linear solution. Otherwise, you know, the amplitude of the linear solution could have been zero. Okay, for both the inflaton field and the graviton field. But in this case, it's, you know, there's an H bar attached to the amplitude of both. So this is a very distinct prediction of inflation, and it just comes from the simple fact that you attach an amplitude to a linearized solution for both inflaton and gravitons. So I think this is one of the most important calculations in physics. It's really blowing my mind, just the combination of GR and quantum mechanics. And these are the people who did this work. So these people did the scalar part, and these primarily Russian did the gravitational wave calculation, which turned out to be very similar to the scalar, in fact simpler than scalar calculation. But my student could have done this now with Mathematica, very easily. They didn't have it. All right, so understanding that part, you can understand why this is kind of a big deal, because this gravitational wave started out as graviton vacuum fluctuations. So if gravity is completely classical, you wouldn't have this. So gravity has to be quantized. Again, and then the amplitude of this fluctuation tells you the energy scale of inflation, because you evaluate this frozen amplitude at horizon axis, and that's related to the Hubble expansion. Okay. So energy scale of inflation is expansion rate during inflation, and it's the gravitational wave amplitude. So once you detect it, you set the energy scale of inflation. So alternative models tend not to generate any gravitational wave. If it did, it tend to generate very blue spectrum, and the high frequency end is severely constrained by direct gravitational wave probes. So the low frequency end is pretty much zero. Okay. So you can just remember this. So alternative models tend to generate no gravitational waves. And string theorists are all excited about the field range of inflaton, which I won't get into, perhaps some other time. But there's a deep connection between the amplitude of the gravitational wave and the symmetry property in quantum gravity. When you're trying to, create a quantum gravity theory from scratch, for example, using string theory. So that's very nice. So there's density perturbation, there's gravitational wave fluctuation, but how do you tell the difference between the two? So after early 80s, people thought this would be impossible, because gravitational wave also generate temperature fluctuation in the microwave background, just like the density perturbation. So after 15 years, several smart theorists finally figured out a way to do it. So they realized the linear polarization state in the microwave background can be decomposed into E mode and B mode. So E mode has no curl, and B mode has no gradient. Okay, just like any arbitrary three-dimensional vector field can be linearly decomposed to two such fields. One looked like electric field, one looks like a magnetic field. And likewise, the linear polarization pattern on the sky have similar properties. You can understand that. So the two patterns have different parity. Okay, so E mode had even parity, and B mode had odd parity. So my undergraduate student at Stanford created this app. All right, there we go. Ooh. All right. So what's going on is we're looking at a screen of ionized plasma, free electrons, pretty well. And the polarization was generated by Thomson scattering, or just the E&M wave moving the electron, back and forth, and re-emitting polarized light. And as you can imagine, if you have a point source unpolarized at the center of the circle, the polarization pattern will look like this, because outgoing wave will tend to move the electron only this way, so when the wave was re-emitted, it's polarized in this direction. Okay? And if you make a circle out of it, it's polarizing this direction, this direction, this direction. It becomes an E-mode polarization, just like what I define as E-mode. Okay, so the nice thing is, whatever you do, however many point sources you have, you're not going to create a curl, a B-mode polarization pattern. Okay? And if you can't do it with point sources, you can't do it, period, because you can create any function with point sources. Okay? So now, that means any linear density fluctuation generate zero B-mode polarization, or the curl polarization. How about gravitational wave? So if you recall, gravitational waves have two polarization. One is a plus pattern, it stretches space this way and this way. And one is cross, stretches space this way and this way. So this is a gravitational wave propagating toward our circle of electrons with polarization, with cross polarization. And again, you generate E mode. If you change the polarization state of the gravitational wave, you get B mode. Okay? So to summarize, any linear density perturbation can only generate E mode. And gravitational wave generate both E mode and B mode. In other words, if you look at this B mode, this curl, you're looking at only gravitational wave, not the density perturbation. So this is a nice property proposed by those gentlemen in 97. So that's very nice, but the polarization pattern is still very small, even though it's unique. Okay, so how small? So the vertical versus horizontal power is different by 1 part in 30 million. Okay, so that's almost by definition an unpolarized light, but it's this is called B-mode polarization for some reason, even though it's too small to be called polarization really. But this is the tough task. Okay, so you need very sensitive detectors, and you integrate for a very, very long time to see the difference between the two. And also you have to deal with systematics. You can't measure the vertical power for a while and then look at the horizontal power, for another an hour, and you subtract the two, you get junk. So you have to do, several layers of modulation, if you will, and make sure you know what the instrument is doing. So sensitivity and the systematics are the big challenges for an experiment like this. We're talking about difference in power for vertical and horizontal by 1 part in 30 million. That's why we justify our experiment at the South Pole. Because it's actually the driest place on Earth because of combination of low temperature and high elevation. It's actually at roughly 3,000 meter altitude. It's extremely cold. All the water vapor in the atmosphere is frozen on the ground. So there's very little left in the air. And water vapor is a big microwave emitter as well as absorber. So you go to South Pole to do this experiment. Also, there's 1 day and 1 night per year, so you get to have very stable climate for continuous observation for 6 months. There's also very good logistical support from U.S. NSF Office of Polar Program. We use C-130 military flights, these planes on skis. We go to South Pole with plenty of leg room. Lots of important experiments were done there. The 10 meter South Pole telescope. This is where we had BICEP1, BICEP2, and soon BICEP3 later this year. And DAISY, the experiment, first detected EMO polarization, quad, and now Keck. All right, so the technology part. So how do you measure the polarization difference in 1 part in 30 million? So the nice thing about searching for B mode, gravitational wave generated B mode, is you don't need very big telescopes because the predicted angular scale is around a degree or a few degrees. And at microwave frequency, that corresponds to 20 centimeter telescopes, not 20 meter telescope, for example. So you can, in fact, put the entire telescope in a dewar, like we did in the BICEP series, BICEP 1, 2, 3, and Keck. All these experiments are part of the very focused program to look for a gravitational wave. Okay, different generations of it. I'll get into those. But all of these use cold refractive telescopes. BICEP 1, BICEP 2, and Keck had 25 centimeter aperture. BICEP 3 gets to about 60 centimeters, but still very compact. But these are all cold telescopes at 4 Kelvin, liquid helium temperature, and the detectors are cooled to a quarter Kelvin. And for the later generation, BICEP 2 and Keck series, we have fully lithographic detectors with mass-produced tiles, silicon tiles. I'll show some of that. But the optics is very simple. It's just 2 lenses and a focal plane with lots of detectors. And that's all we do. It's also very similar to a condensed matter low temperature experiment, if you will, except when we finish it, we ship it to South Pole when we start observing. Also, we need to have a big window to emit microwave radiation. We can't just block it off and let the sample get cold. We have to open it up to the ambient radiation, hundreds of watts, and yet keeping the detectors cold. So there are lots of challenges.